All right, hello. We're going to go Chapter 1, Section 2, Limits. Okay, our objective here is finding limits graphically and numerically. All right, our first example for f of x graph below. You see we got a piecewise function of some sort down there. Okay, we're going to find each limit graphically. All right, so again, doing this graphically, we don't need to know the equations of the different parts of that piecewise function. But anyway, here we go. All right, a little bit of notation, sort of translation, I guess you could say. If you look at the right-hand side, I'm going to zoom in on it real quick here. Okay, you see here it's got lim f of x, and below that it's got an x with an arrow and -4. All right, the way we're going to pronounce that is, well, lim, I think is pretty obvious. That's going to be the limit right there. Okay, so this is the limit of f of x. So the limit of f of x, and then we're going to say as x approaches -4. That's what the arrow means, is approaches. So seeing that mess of stuff right there, we're going to say the limit of f of x as x approaches -4, or alternatively, you could say the limit as x approaches -4 of f of x. So you can kind of mess with the order basically. It does mean the same thing, but anyway, that's what all that craziness means. All right. Now the big idea behind a limit in general is the limit is the y value that your function approaches as we approach whatever x value we're talking about. All right, so that's a little bit funny to get used to at first, so let's kind of take it slow on this first one here. Okay, for the one that's currently highlighted, I've got the limit of f of x as x approaches -4. All right, so I want to kind of take a look at -4 on my graph, the x value -4, so that's right here, and I go ahead and find my function, which I can see kind of in the second quadrant here. All right, now as x approaches -4, so as the x values get close to -4 from both sides, I'm kind of doing that, and if I think about where that is along the function, that means I'm tracing along the function coming this way, and I'm tracing along the function kind of coming that way. Notice that I'm getting very, very close to the x value of -4 as I kind of squeeze in, if you will. And I can see by what's labeled in the graph that that's the point -4 too, but notice it's a hole. However, I don't care that it's a hole because, again, my objective here is to find out what y value I'm getting really, really, really close to as I get really, really, really close to the particular x value. And as I'm getting really, really, really close to an x value of -4, I'm getting really, really, really close to a y value of 2. So therefore, the limit of f of x as x approaches -4, in this case, is equal to 2. Okay, and again, I don't care that there's a hole at 2. That's not what I'm asking about when I'm asking for a limit. I'm asking, what I get really, really close to in terms of a y value as I get very, very, very close to a particular x value. All right, hopefully that made sense, but let's keep going. All right, the next part of my example here is the limit of f of x as x approaches 1. All right, so then we have same basic idea. We're going to take a look at what's happening at 1. All right, so zooming in just a hair. We've got, of course, an x value of 1 right there. That's not officially labeled, but I think it's obvious enough. Okay, now we do have a problem, though. As I come towards an x value of 1 from the left-hand side of my graph, I'm kind of cruising along here, and I'm getting pretty close to a 4, it looks like, in the y value. However, if I'm coming in from the right-hand side of things, I'm kind of tracing this curvy sort of thing here, and I'm getting very close to what looks to be about -2. All right, now that's a problem because I don't match. Okay, now if we have that situation where we don't match, what we're going to say is that limit of f of x as x approaches 1 in this case, this guy does not exist. Okay, now if you'd like to abbreviate that as dne, that's fine. Okay, the official answer is does not exist, and that's what you will see on the AP exam, but for the purposes of our class, if you want to abbreviate that as dne, I'm totally okay with that. All right, moving on. All right, we've got the limit of f of x as x approaches 4.5. All right, so again, let's change colors. Let's go pink. All right, so 4.5 here, we can see on the graph that 4.5, bing, right there. Okay, sorry, the pink doesn't show up against the red very well, but there it is. Okay, so here's my 4.5 in the x direction, and we can see pretty clearly there that our function is hitting 0 at that point, and that's all good, but again, the whole idea is what do we get close to as we get close to the x value, and as we get close to the x value of 4.5, I'm getting really, really close to 0, so good enough. So basically the point is you might have a function that actually hits that particular value, and that's all good, but it's definitely not a requirement, as we saw in the first example that we had there. All right, last one down there. Okay, I've got the limit of f of x as x approaches 6. All right, so again, taking a peek at 6. So here's our 6. And all right, cool. Hey, look, we got 6, 2, so the limit must be 2. All right, so you go over here, you say 2, and then your teacher grades it, and you're wrong. All right, so again, I don't care what the actual y value is at the exact x value. I care about what you're getting close to as you get close to the x value when we're talking about limits. So I need to kind of take a look at the function as I'm coming in from the left-hand side and the right-hand side of this guy. Okay, we can see that we're getting very, very, very close to a y value of 5. Okay, even though, again, that's a whole, and even though that the function is actually defined at 6 to be the number 2, we don't care about that. We want to know what we're getting close to in the y values as our x value gets really, really, really close. So we're worried about 5.9999 and 6.0001. What's it doing for those x values? So the limit of f of x as x approaches 6 is actually 5. Okay, again, don't let the actual point there fool you. If that 0.62 wasn't on the graph at all, I'd still get the same answer. Okay, very much like the first one that I did in green. All right, but there's a quick summary of what it takes to do limits graphically, so when you have a picture to work with. All right, let's keep moving on. Okay, we've got f of x equals x to the third plus 64 over x plus 4, and I want to determine the limit of f of x as x approaches -4 numerically. And, well, as you can kind of see here, okay, we're going to require a table for this sort of thing, so we can kind of think our way through it. Okay, now if you graph that function and pull up a table for it, you will quickly see that at -4, you have an error. Okay, and that should be obvious enough by the equation having an x plus 4 in it, so you're going to get a 0 denominator, so there's where the error comes from. All right, and then to get the answer to this, what you can do is start figuring out what is my y value as I get really, really close to that, because -4 is the only bad x value we're going to have. So if we have like -3.9 and -4.1, you can see in the table, we should be able to get some other numbers. All right. So if we go to our table and to change our table settings, and if you don't know how to do that, please ask in class. Okay, for -4.1, we should get a value of 49.21, and for -3.9, we got 46.81. Okay, so basically that's telling me my limit is somewhere between 46 and 49-ish, but you know what, that's not overly accurate, so maybe I should go to a smaller delta table or step, depending on your model of calculator. And so if we set it to 100th, we can take a look and get 3.99, -3.99 that is, and -4.01, and we get 47.88 and a 48.12. Okay, at that point it might be pretty clear that, hey, it's somewhere between 48.12 and 47.88, so it's probably something like dead on 48. But if you just want to be sure about it, go one step further, and at the -3.999 with a step or a delta table of 0.001, we get ourselves a 47.988, and on the other side of things we get ourselves a 48.012. Okay, so once you've made it that far, it's probably a little more obvious, but again, you can keep kind of running things out and going for a smaller delta table or just smaller step. But ultimately what we've got here is certainly the limit as x approaches -4 of the function in question is going to equal 48. Moral of the story here is whatever you have, come up with some delta table that you think is going to be good enough to give you a good picture of what's actually going on in terms of the numbers. And then if you don't get it based on what you initially thought your delta table should be or your step should be, and then change a little bit until you get something that seems like a good result. It does take a little bit of playing around, a little bit of experience for that, but anyway, that's the deal there. All right, let's move on. Okay, now we already actually saw one example of this, but there are limits that do not exist, and there are 3 basic scenarios where that occurs. Okay, one is the behavior differs from the left and the right, and that's kind of the one we already saw. All right, so I'll do this one relatively quickly here. All right, so first of all, graphing on a calculator technique for f of x equals 9 over x, we want to determine the limit as x approaches 0 of that function. Okay, well, if I graph it on a calculator, let's do that as 1. All right, the graph of this guy will look something like this. Pardon me for my rough sketch right now, but it will be enough to get the job done. All right, so there you go. Now, we can clearly see that as we approach x equals 0, which is, effectively, the y-axis right there, on the right side of our graph, that thing's heading towards positive infinity. On the left side of the graph, the function is heading towards negative infinity, so that's clearly why we have a does not exist scenario there. Okay, now admittedly, if you don't have the calculator at your disposal at that point, and for example, if you're in a non-calculator part of the exam, you have to be able to think your way through it, although it'll look pretty similar to what I just did as far as the graph goes. So option number 2, think through it. Okay, you can kind of go, hey, well, if I'm plugging in values into 9 over x, in case you don't know what that looks like, you know, just intuitively or whatever. All right, you can say, okay, cool. Well, values that I can pick that would work out nice would be like 1, 3, and 9. All right, now if I plug in 9, I'm going to get a y value of 1. If I plug in 3, I'll get 3. And if I plug in 1, I get 9. And then you can start thinking, hey, well, if I plug in something like 0.5 or a small decimal, if I take 9 divided by a small decimal, I'm going to get a great big number. So this thing's going to clearly keep going upwards. And then on the other side of things, if we take the negative versions of these guys, I don't think I need to go all the way to the 9 at this point. All right, I'll get a negative 9. When I use negative 1, I'll get a negative 3 at 3. And again, if I pick some negative small number, 9 divided by negative small number is a really big negative number. So I can see that this guy's doing something like this. And again, same basic idea. Left side and the right side are definitely doing 2 different things. And I didn't say it already, but clearly, hopefully, you look at that and think, okay, well, 0 is going to be undefined. So you definitely won't have a point for a function at 0. So you're definitely going to end up with something like what I did there. So again, either way that works, and you get does not exist. All right, now we might have oscillating behavior, and this is one you may not have ever seen before, so hang on. Here we go. Okay, for f of x equals cosine of 1 over x, I would have determined the limit of the function as x approaches 0. All righty, well, if you go ahead and graph this guy on a calculator, okay, I'm going to go with negative 1 and 1 here. Okay, what this guy actually ends up doing is coming across kind of asymptotically, if you will, at 1, and then as it gets close to the origin, it kind of dives down, comes back up, and then starts doing some craziness like this, and then kind of follows through and eventually levels back out and goes off like that. All right, so if I'm looking for x approaches 0, you know, I can kind of, well, you can zoom in on your calculator better than what I can do based on my hand-drawn thing there, but if you keep zooming in, all you're going to see is this big horrible mess. So it's bouncing between 1 and negative 1 the whole time. It's just this colossal garbagey mess of stuff, and it never really zeroes in on a particular value. So that's what I mean by oscillating behavior. It keeps going back and forth between 1 and negative 1 and kind of never settles down to anything. So that's where that guy would be. It does not exist. Okay, now the think through it version of this, I confess, is a little bit trickier, but here we go. If I'm doing cosine of 1 over x, okay, again, keeping in mind that as I'm getting close to 0, I'm plugging in a tiny number there for x. But if I plug in a tiny number for x and do 1 over that tiny number, I get a great big giant number. So if I start thinking about unit circle-y stuff, as I plug in a number that's really, really, really small, I get 1 over really small, so I get a really big number. And cosine of a really big number could really end up being anywhere in the circle you want it to be. Let's say it's over there to cover up my really bad drawing of a circle right there. But then I can always pick another number that's slightly smaller for x, and then I'd plug it in, and again, then I would take 1 over that, and I get some other huge number, so who knows, maybe it ends up way over here. Okay, so as you keep plugging in really, really tiny numbers, you keep getting a really, really, really big angle measure for your cosine, and then who knows where that thing's going to land on the circle. So there's really no way to predict it as you keep getting closer. So again, does not exist based on that thought process well. Alrighty, let's go to option 3. Okay, we get unbounded behavior, and if the last one was blowing your mind, hopefully this one is a little bit nicer on your brain, but here we go. All right, so for f of x equals 4 over x squared, we're going to determine the limit of f of x as x approaches 0. Okay, now again, option 1 is graph on a calculator because, you know, a picture is worth 1,000 words, so here we go. And if we go ahead and graph this, we end up with something that looks a little bit like this. Okay, so there it is. So we can graph on the calculator. Okay, now again, I'm interested in 0, and 0 again will be undefined in this scenario. So we don't have 0 comma something as a point, and so we're going to have like an error message over there. So actually let me fill in my table at that point. Definitely an error there. Okay, but what we do have is, yeah, this thing is shooting off to infinity, and infinity technically isn't a number, it's a concept. So the limit needs to be a number. I do confess later in the year we're going to start saying infinity is a good answer, but at this point in the year we're going to say, ooh, this does not exist because infinity technically is not a number. There we are. Later, like I said, we'll give infinity an answer and be just fine, but we have to kind of work through some other stuff to get there first. All right. The option 2 of think through it is kind of what I've already said. You're looking at 4 over some tiny, tiny, tiny number, and even if you square a decimal, something less than 1, you get something even smaller. So if we take 4 over one of those small numbers as we're trying to approach 0, okay, it's going to be equal to some huge number, and again, effectively heading all the way to infinity, but that's a concept, it's not an actual number. So again, we're in a it does not exist because it's something we can't actually calculate. So there we are. And then of course, if you want to go to the table, that's option 3 over here. Let's change colors one more time. Okay, and again, if we set up our calculator, I've just got to set it up where our table step would be 0.01. Okay, at 0.01, we would get an answer of 40,000. All right, if I go to the 0.02, it works out to be 10,000 in both directions there. And then we'd work out to be 4,444.4 in the other ones. So you can see as you're far away, you are getting smaller, and as you're getting very, very close to 0, we are getting some pretty huge numbers. And again, we could go with smaller decimals and get much larger answers if we wanted to, but I think that's good enough to get the point across. Alrighty, so there's 3 different ways that you could have a does not exist scenario, and several different ways to get that answer depending on the tools available to you or your particular choices. All right, so here we are. The previous 3 examples all use limits where x approaches 0. Okay, now please understand that was not necessary for the limits not to exist. It just made it a little bit easier for the problems to look not quite so messy. All right, the assignments are over there on the right. Section 1.2, we're page 54, and 1 through 27, odds. In this class, every assignment I give you is going to be odds unless I specify something other than that, so I don't have to write odds 350,000 times as the course goes on. All right, but anyway, there's your official first video. Hopefully it made sense, but if not, ask any questions you want to in class, and I'll be happy to answer them. See you there.